Well, I'd like to talk to you today about a technique called ASSR, or Auditory Steady State Response. It's really an electrophysiological method of acquiring an audiogram. It has some similarities to ABR. For example, ASSR is an electrophysiological measurement, as is an ABR. And actually the difference is that this response is to very rapidly presented stimulus, much more rapidly than you would do in an ABR. The goal of an ASSR is to create an estimated audiogram, or an electrophysiological audiogram. ASSR relies on a statistical algorithm to detect whether a response is present. You don't actually see a waveform like you do on an ABR. And historically, ASSR has suffered some problems. There were two manufacturers, and as these systems developed, they had inherent problems. The earliest form of ASSR was a technique called phase coherence. I'll talk about that technique, and it's a technique that's used to detect the response. A later system actually used a different technique, FFT, fast Fourier transform. It's a means of doing a spectral analysis on the response and detecting magnitude differences in the response at certain frequencies. I'll explain that to you. And there's a more recent system that actually uses both strategies, the phase coherence and the FFT, and some other techniques that make this even a more viable test than it was. So let me just go through a couple of ways that ASSR and ABR are similar. Okay? This will kind of make us understand it a little bit better. Well, both record bioelectric activity. They're both electrophysiological tests. And they both use a similar, in fact the exact same, electrode montage. And both are classified as auditory evoked potentials. Okay? So the CPT code would be the same. Both use the same type of transducer and the same type of equipment. However, ASSR is always an option. It isn't standard on auditory evoked potential equipment. And here are the differences. ASSR uses amplitudes and phases of the response in a spectral domain rather than a time domain in order to make a judgment whether a response is present or not. And ASSR uses a very rapidly presented stimulus, presented at 80 times per second or more, something that we wouldn't do with an ABR. Okay? ABR is dependent on amplitude and frequency. This amplitude and latency here, we don't really care so much about amplitude and latency, especially latency, it has nothing to do with it. And in ABR we use peak detection. Where is wave 1, wave 3, wave 5 especially? With this, there is none of that. And ABR is evoked using brief stimuli at relatively low repetition levels. In fact, this stimuli is presented so quickly that it appears to be a steady state, hence the name steady state response. Okay? A few more differences. ASSR is not analyzed by looking at a waveform. You don't even see a waveform. It uses a sophisticated mathematical algorithm to detect the presence of a response. And in fact, with ASSR, we can do several frequencies simultaneously. Actually, typically 4 frequencies are done simultaneously. And we can also test both ears at the same time. That's a real advantage. And ASSR is more efficient than using tone bursts and ABR to do frequency-specific testing, especially at low frequencies like 500 Hertz, and especially for patients that have severe or profound hearing losses. The output of the typical ASSR system is 120 dB NHL, as opposed to an ABR, which may not be able to produce levels anything like that. Okay? If we were doing an ABR, you see what we would have to do? We would have to decrease intensity until we could no longer identify a wave 5, and that would be the threshold. We would then apply a correction to it, and we could come up, if we did at least the 4 frequencies, 5, 1, 2, and 4, we could come up with an estimated audiogram from that, okay, by doing a latency intensity function like this. Well, ASSR is going to be a little bit different. And we have addressed the problems that ASSR has had in the past, okay? One of the problems that it had is that it was inaccurate when it determined a threshold on a patient that had a moderate hearing loss, a mild hearing loss or normal hearing. In fact, we never used it on patients that were suspected of having a mild loss or have normal hearing, because it overestimated the threshold, made the hearing look worse than it really was. Another problem that we had was that we had to reserve this for patients that could be and were sedated. Not just sleeping, but sedated. With the new technique, you'll see we won't have to sedate the patient. We can do them in a state where they're sleeping. With the typical type, we had to use sedation and nothing else. And this has been improved by doing 2 things. A better detection technique of actually detecting the ASSR response, and a way more efficient stimulus. So this is a different type of stimulus. Put them both together and you've got a way more viable system. Okay? Here's the systems that existed in the past and still exist. The first system that we have experience with is the Grayson Stadler Viasys. They were owned by Viasys at the time. They're not owned by Viasys anymore. They're owned by the William Demont Company. But anyway, Grayson Stadler Audera has an ASSR option. It was developed in Melbourne, Australia by Barbara Cohen-Wesson and her colleagues. The next system that appeared on the market in the United States was the Biologic Master. And that came from a Canadian project that was developed by Terry Picton and his associates. And this is the way that the Grayson Stadler product, the Audera, detects an ASSR response. It's called phase coherence. If this was the response that was present in a patient's EEG while they were stimulated by a very, very rapid rate pure tone, okay, then this response would be considered phase coherent, because of all the responses that are here, you can see there's at least 10 of them there. They are negative at the same time, and they're positive at the same time, and negative at the same time. So their phase is coherent. And if we were to plot these as vectors, it would look like this. Okay? We're just comparing the phase of one sample EEG response to the phase of another sample. And we're just plotting a vector that represents the difference between the phase of one versus the other as we compare them. And if they're all clustered tightly like this, they're said to be phase coherent. And if they are phase coherent, then you can depend on a response being present at that particular frequency and at that particular intensity. And here's how it looked on the piece of equipment. This is the Audera equipment, and this is the vector plot. And this is really all you see while it's running. You see these lines appearing on this vector plot, and it's comparing the phase of the response with the phase of the stimulus. The phase of the stimulus is this white line, and I don't know if you can see this on this video, but one of these vectors is white, and it's right here. The rest of them are being compared to that. And if they cluster, in other words, they're all similar in phase with one another, then they are said to be phase coherent or phase locked. And at the same time that these vectors are appearing on this vector plot, there's a probability plot that goes on here. And this starts in the lower right-hand corner at 0. This is probability from 1 to 99.9% probability that a response exists. Okay? So it goes from 0 to 99.99. And this is time, right, between 0 and 64 seconds. So hopefully what you want to happen is this line increases up as more and more of these are being plotted and are being analyzed to be similar to the previously plotted ones. This line will extend up, and once it gets to 99.99, the phase coherence is indicated, and that indicates to the system that a response was present at that frequency and that intensity. You can only do one frequency and one intensity at a time when you use phase coherence like this. Okay? So that, if you saw a vector plot that looked like this, all randomly presented, then there would not be phase coherence. If you see them clustered like this, then there is phase coherence. And on the equipment, this would be one, this would be an intensity at which there was no response detected. Notice that these vectors are plotted randomly around. They're not closely related one to another. And our probability plot just wavered and finally timed out as no response. This is a random response rather than a phase-locked or phase-coherent response. Okay? So, once you've done both ears, and once you've found a threshold for the 500 hertz, 1000 hertz, 2000 hertz, and 4000 hertz signals, then the system would then apply a correction and come up with an estimated electrophysiological audiogram. This system works well on patients that are sedated, and it runs pretty quickly, and it works well on patients that are sedated, and also patients that have moderate or worse hearing, moderate, severe, or profound hearing. The output does at each frequency go to 120, and you can accomplish the test in just under an hour under sedated conditions when the hearing is in that status. Okay? There's many uses worldwide, and it is, people like it when it's used in its proper application. The biologic product, and they still have this as an option on their auditory evoked potential systems as well, uses a different methodology. Same stimulus, okay, which is simply a pure tone that's modulated or turned off and on at a very, very fast rate. When you do that, naturally, you stimulate the cochlea at a specific point at whatever frequency. We call it the carrier frequency. That's the frequency of this pure tone that is pulsed or presented very rapidly. In this case, 81 hertz. Okay, this is a 1000 hertz pure tone that is being pulsed or presented 81 times per second. Okay, stimulating an area of the cochlea right at 1000 hertz. And if we measure the patient's EEG while he's being continuously stimulated by this auditory steady state response, steady state for continuous stimulation, and we took the EEG results, right, and we averaged it, the noise would eventually average down, and we would find a spike in the noise, the background noise level, and guess where that spike would be? Not at 1000 hertz, the frequency of the stimulus, but at 81 hertz, the frequency of what we would call the modulation, how many times per second we're presenting that stimulus or pulsing that tone. Okay? Does that make sense? Let me carry it a step further. Look at this. Suppose we wanted to be able to stimulate the ear with 4 frequencies at once. How could we do that? We can, because there's a combined signal. Here's 500 hertz. Here's 1000 hertz, 2000 hertz, and 4000 hertz. And here's a combined signal of all 4 of these. The difference between them, besides their the difference in their frequency, what we would call the carrier frequency, that's the test frequency. The difference is that the modulation rate, how many times per second we pulse or turn off and on that pure tone, is different for each. Like if this one's 81, this one's 83, this one's 85, and this one's 87 hertz times per second. Well, if we did that, we would stimulate 4 discrete areas on the cochlea representing these 4 frequencies. And if we then took the patient's EEG and averaged it, and as we were doing that, did a spectral analysis or an FFT on it, we would find 4 spikes in it, and those spikes would be exactly at those frequencies of what we call modulation frequencies. The 81 hertz, 83 hertz, 85 hertz, 87 hertz. Okay? Hope that makes sense. Let's take it even further. Look at this. We want to do both ears at once. So 4 frequencies in the right, 4 frequencies in the left. That's 8 different stimuli all together being presented simultaneously. But we're using, look at this. I hope you can see it. 8 different modulation rates. 77 hertz, 85 hertz, 93 hertz, 101 hertz, 81 hertz, 89 hertz, 97 hertz, 105 hertz. And what do we find, right? We stimulate both cochleas at 4 discrete frequencies, and we find 8 spikes in the averaged and spectrum analyzed result of our EEG. We find 8 spikes, 1 for each of these 8 frequencies. 4 for the right, 4 for the left. Okay, this is an efficient way of doing it. The problem is that you've got to do it forever. You've got to average for a long, long time. Advantage, 4 frequencies at once, both ears at the same time, but a lot of averaging time to get the noise down low enough where you can actually see these spikes. Looks like this eventually. Okay, here we did both ears. Well, what do we do here? Yes, both ears, 4 frequencies each ear, okay? And you see these spikes that existed. And the machine determines whether it actually exists there. It uses signal-to-noise ratio to determine whether a response is present. And so these responses were all present at 80 dB here. At 70 dB, still all present. Notice at 60, a couple of them dropped out. At 50, a couple more dropped out. At 40, even more. By the time we got to 30, none of them can be distinguished as being above the noise by the algorithm. And we end up with an audiogram. And you say, how well does all this relate to hearing? Pretty good, okay? To behavioral hearing. These are the correlation rates. You know correlation is perfect if it's 1.0, all right? So how good is the correlation between the corrected ASSR? There is a correction factor that's already factored in by the machine. Okay, 0.86 at 500 hertz, 0.94 at 1,000 hertz, 0.96 at 2,000 hertz, and 0.98 at 4,000 hertz. Okay, pretty good correlation. Right? If it was perfect correlation, all of these plots would be on that red line. Okay? And the correlation would be 1.0 then, instead of something like 0.98. All right, so we have something here. Okay? We find a spike within all of the noise in a patient's EEG. By noise, I mean legitimate EEG, but it has nothing to do with the stimulus. This one has something to do with the stimulus. Notice also that there's some more spikes standing up that are way above the noise. What are they? They're harmonics of this. Okay. Well, what if, when we tried to detect this response, we not only looked for this, but we also looked at these harmonics? Okay. Would that help? Well, here's the harmonics. If we're using a modulation rate of 90 hertz, here's the first, second, third, fourth, etc. harmonic. Look at all those harmonics. That's a lot more that can be used to detect a response. That's our new detection technique. Our new detection technique uses not only the frequency of the modulation, which in this case we call the fundamental frequency, but it uses all the harmonics as well as that. That gives it more power and allows this response to be detected quicker. And at the same time, we are using phase coherence as well. Okay, so this helps. Okay, so this is how we can reduce time. First, a more efficient stimulus, which I'll talk about next, as well as a more efficient detection technique. Right, it's all using statistical algorithm. Okay, so this stimulus, how is this stimulus better? Well, for one, it's an improved stimulation when you get to the patient's threshold. It's an improved stimulation. We actually get a more synchronous firing of neurons in the auditory nervous system because it stimulates a wider area. It stimulates a wider area, and you might say, well, it's not so frequency specific then. Well, neither is a tone burst, okay? This stimulus, by the way, is going to be called a chirp versus a tone burst. Well, here's the response of the tone burst, okay? And you see that it's actually even wider than the chirp, but it's shaped differently. This part that actually stimulates the cochlea near threshold actually is wider than the part that's going to stimulate the cochlea near threshold with the conventional ASSR stimulus. Okay? All right, so keep that in mind, and here's a chirp. The chirp could be used for ABR and ASSR. And the advantage is that it stimulates the cochlea in a more synchronous way than a click, or certainly than a tone burst. Reason why is it is a band of frequencies. Whether it's a wide band, which would replace a click, or a narrow band, which would replace a tone burst, no matter which it is, wide band or narrow band, the low frequencies are presented first to the cochlea. They are given the time that they need to travel to their destination at the apex of the cochlea before the mid-frequencies and the high frequencies. So they all arrive at their destination at the same time and travel down the auditory nervous system at the same time. That's not what happens with a click or a tone burst. There isn't a synchronous firing. Everything arrives at a different time and starts traveling down the auditory nervous system at a different time rather than together. And so it's an asynchronous response. This is a more synchronous response. Okay? So I have a chirp illustration here that I'm going to make. So, this is the cochlea. This is the base. This is the apex. Let's see what happens with a click. Here's what happens with a click. I'm going to step it through and try to show you this at the same time. Okay? Here comes the click. All the frequencies, a click is a broadband stimulus. All the frequencies are presented at once. If it's a tone burst, it's the same thing. There's just less frequencies because a tone burst has a much narrower band than a click. Okay? Anyway, whatever frequencies they are, they travel. Okay? The low frequencies have much further to go than the high frequencies. High frequencies are already there. Okay? Now, as this continues, all right, high frequency already arrived and is started down the auditory nervous system. Next highest frequency started. Next highest frequency started. Next highest frequency started. And now finally, the lowest frequency arrives at the apex and it starts. Notice they all start down the auditory nervous system at different times, arrive at the inferior colliculus at different times, and so you have an asynchronous responses. If I can just finish this out, here's what we got. We got the high frequency response occurring faster. This is time here in milliseconds. This high frequency, the response to the high frequencies occurred before the mid frequencies and way before the low frequencies. So what you get is a composite of those. Okay? All right, fine. We've had that all along. How is this the chirp different? I'm going to show you. Now we'll use the chirp instead. watch as I scroll through here. With the chirp, the low frequencies go in first, okay? Then the mid frequencies, then the high frequency. Timed so that they all arrive at their points of excitation at the same time. And therefore, they all start traveling down the auditory nervous system together. Right? This is synchronous rather than asynchronous. They all fire at the same time. Notice all wave 5s occur all lined up at the same point in time, and what we get is a composite of those in the ABR, and the response that we get from a chirp is always twice the amplitude of what we would get with a click or a tone burst. The chirp stimulus is what we're using in this method of ASSR. Okay, and so suppose you wanted to use this method to detect a response in a patient. Could be even doing a screening on an infant. Well, let me just show you some test results. Okay, this is just comparing testing a chirp with a click. 49 normal hearing younger adults, okay, college kids. And what were the results? Okay, well, the detection time for the chirp was 30 seconds, the mean detection time, okay? And the click was 72 seconds, okay? That's at 30 dB. At 50 dB, the chirp was detected in 23 seconds versus the click, which it took 40 seconds to detect, all right? So the time that it takes to detect the response is cut basically in half or better. Why? Because if everything's based on signal-to-noise ratio, well, with a bigger response, you can achieve an adequate signal-to-noise ratio to determine the presence of response much quicker. Okay, Jay Hall used to say, this response is like a needle in a haystack. Okay, well, and all the averaging forever and ever on end is in order to get rid of the haystack and find the needle. Well, suppose you can make that needle into a pitchfork, much easier to find in the haystack. Okay, here is a study on newborns. We actually used this technique, an ASSR, but with a chirp, a rapidly presented chirp instead of a tone, and used it to detect whether a patient will pass or fail this screening. Okay, so like an ABR screening, but with a better technique. This is to compare using a click, which is typically used, and we used a click at 40, just to give it an advantage, a clear advantage, and the chirp at the normal screening level of 35. Okay, we had two groups of newborns, each with about 1,800 ears. Okay, here's what we got. All right, with the click, using the best techniques possible of delivering the stimulus and detecting a response in the normal ABR screening, okay? And we're cheating, we're giving the click an advantage, 40 dB, all right? Well, 95% of the time we're able to detect a response in these normal patients, 95.4% of the time, and it took an average of 42 seconds to actually detect the response. Okay, well, pretty good. But what if we used a chirp? Okay, look at this. Now we've detected it 96.3% of the time, and we did it in an average of 28 seconds instead of 42 seconds. Cut it up the time it takes to detect the response in half. Okay? All right, well, I wanted to tell you about chirps, because chirps are great for ABRs and frequency-specific ABRs, much better than clicks and tone bursts. And the equipment will have both anyway. And several pieces of equipment have this. The Grayson Stadler Audera has chirps for ABR. The Interacoustics Eclipse also has chirps for ABR. And I hear that Biologic and VivoSonic are putting chirps on their equipment also. Everybody's excited about this. All right. Now, chirps for ASSR? Absolutely. Here's the bandwidths of the 4 frequencies of chirps that we're using. Rapidly presented chirps instead of a rapidly presented tone. 500 hertz, 1000 hertz, 2000 hertz, 4000 hertz. See these narrow bands? Very reasonable, and if we compared those to the narrow bands of the typical tones that we use, they would be about the same. They just wouldn't be as flat on the top. Okay? That flatness on the top helps us. Okay, helps us actually get a more synchronous response, as well as other things. Okay, so what we've done with the new equipment is 2 things. We've used a better method of detecting the ASSR. Okay, we're using both amplitude and phase detection. So we're using both methods, FFT and amplitude and phase coherence. And besides that, we're doing this with detecting the 6 harmonics plus the fundamental frequency, rather than fundamental frequency only, and then we are using the chirps instead of standard tones. So that way we cut the time way down. Okay, what piece of equipment does it like this? It is the Interacoustics Eclipse. This is the best ASSR I ever saw, and I've been with this since the very first day the very first instrument came out, right? That Melbourne, Australia project. Here's how this works. Both ears are tested at once. 4 frequencies are tested at once. All this simultaneously. And if you looked at any one frequency, okay, here's one particular frequency. It happens to be 4000 hertz. And is there a response or not? All right. Well, let's look and see what they did here. They're looking for a threshold. Okay. The stimulus was applied at 55 dB. And see this red line right here. Okay. It started at 0. This is probability, by the way. From 0 to 100% probability that a response is detected. It's a chirp, rapid chirp, and it is this complex detection method. Right? Look how fast. These are seconds. I'm sorry, these are minutes here. So within, I guess it's about maybe 20 seconds right here at 55, response present. And then at 50, all right, well, it kind of meandered around before it got to 100%, and it took it a minute. All right, reduced the intensity to 40. About a minute and 10 seconds, maybe a minute and 15 seconds, a response was detected. Got to 30, and this is what happens when there's no response. It never makes it to the 100% confidence level of a response being present. Now remember, at the same time, both ears are being done, 4 frequencies at once are being done. I just showed you one at a time so it would make sense. So you see the stimulus intensity, the plot of probability that continues as the test is continuing, and the green response, meaning it made it to 100%, and therefore a response was present at that frequency, at that intensity. Red, no response. Okay? All right. So here's a normal ASSR, a normal hearing patient. Here's right, here's left. This is 500 hertz, 1000 hertz, 2000 hertz, and 4000 hertz. And you see here they did, and this would be kind of typical, 65 dB, then it went down to 45, then 30, then 15, then 10. And you see less than around 1 minute they get these responses at the higher levels, a little bit longer, approaching 2 minutes when they got down to 30 dB. And when they're getting close to threshold, okay, so we're approaching 5 minutes at 15 dB and approaching 8 minutes at 10 dB. Okay, at 500 hertz, the hardest frequency to do. What if you were doing tone bursts? All right, and remember, while this was going on, all the rest was going on simultaneously, the other ear too. And you see here at 1000 hertz, they got it at 15 and not at 10. Here at 2,000 hertz, they got it at 15, not at 5. Here they got it at 15, this is 4,000 hertz, not at 5. Anyway, they determine threshold like this. This is easy, it's just plots of probability that advance during the stimulation period. All right, and then the result, an estimated audiogram. This grayed out one here was the actual threshold of the ASSR response. A correction was made, and these are the estimated behavioral thresholds. And look at this, I did this on a normal hearing patient. Wouldn't even try it on a conventional system. This is the Interacoustics Eclipse ASSR. It is the most viable ASSR in the world. In fact, it's the only one that's really viable to me anymore. Okay, somebody with a hearing loss. Here's a binaural loss. Okay, here 55 dB, and he didn't get it, only at the higher intensities. Okay, 55 dB, 65 dB, 65 dB, 80 dB, etc. Okay, and audiogram here, there you go. Okay, the correction. The system also gives you the numbers. This is another way to look at it. Instead of looking at these probability graphs, here's even a simpler way. This is presented at the same time. For example, at 55 dB, which is where we started this test, expecting to find a moderate, severe, or profound hearing loss on this patient. And at 55 dB, we got no response at any. Red is no response, green is response. We got no response at any of the 4 frequencies on this ear. And when we moved to 60, we got a response at 3K. Notice that's green instead of red because it was a response, and the number in it is 100, meaning 100% probability that a response was there. Here it's 38%, 14%, and 60%. No, not reaching 100. At 65, got responses at all 4. Well, I hope you can see that ASSR is now an extremely viable way to determine an audiogram, a frequency-specific audiogram at 500, 1000, 2000, and 4000 hertz on patients where this method would have to be used. It's now viable. Viable meaning it can be done on patients with all hearing levels, not only reserved to patients that have a moderate, severe, or profound loss. It can actually be done in a very reasonable amount of time on patients that have maybe a moderate loss, a mild loss, or even normal hearing. And the patient can be sleeping or very calm. Okay? Now, of course, you couldn't do this on an active patient. That would not be possible. ASSR was never possible on an active patient. But it was also never possible even on a sleeping patient. They had to be sedated. You had to bring that EEG down very, very, very low in order to be able to do this. They had to be totally and absolutely sedated. Now with this method, using both of those techniques, the chirp stimulus, which gives you a stronger response because of more synchronous firing of the auditory nervous system, using that as well as this advanced detection technique, we're able to actually accomplish a couple of things. One is we don't have to bring the EEG down as low. We can do it on patients that are either sleeping or very, very calm. Right? I don't know that that's possible on pediatrics, but a sleeping baby for sure. Okay, doesn't necessarily have to be sedated. That's one advantage. Second advantage is we can do it on patients with normal hearing, moderate, severe, profound, any level of hearing loss, rather than severe and profound only. And the time that it does take to do both ears, 4 frequencies, as I said, this is all done simultaneously, the amount that it takes will be half the amount of time that it would take for the previous technologies. In other words, you'd accomplish this in 30 minutes instead of an hour. And sometimes it would be an hour and a half with the original technologies. So I hope that gives you a good understanding of both what ASSR, auditory steady state response, is all about, how it works, what are the different techniques, and what is the new technology that has made this test go from a useful tool to an even more viable and useful tool for a larger population. Thanks a lot. See you next time.